Underneath the quiet hills of California in the spring of 1984, federal agents quietly surrounded a climate-controlled laboratory. They were not raiding an illegal drug cartel or stopping a foreign spy ring. Instead, armed agents were seizing control of a 7-ton slab of gray granite floating on a pressurized cushion of synthetic oil. Mounted to that heavy stone was a machine named the Large Optics Diamond Turning Machine, known as LODTM. Built by Lawrence Livermore National Laboratory, this machine had one main job: rotate metal parts and cut them with a single natural diamond tool. But its accuracy was so absurdly absolute that ambient air temperature shifts of 1/100th of a degree would ruin a cut. Even the body heat of a human standing 2 feet away transferred enough thermal energy through the air to warp its tolerances. Federal officers immediately locked the internal optics and control algorithms under top-secret security. The United States government treated a metalworking lathe with the exact security protocols reserved for thermonuclear warheads. Consider what that means. National power did not depend only on nuclear physics or microchips. Power depended on mechanical geometry. Whoever controlled the cutting tool to within the width of a light wave held the master key to global power. Welcome to Rivet and Rebar, where we dig into the industrial giants and mechanical sagas that quietly built the modern world. If forgot industrial history and extreme engineering inspire you, take a moment to like and subscribe to the channel right now. Long before microprocessors and laser feedback loops existed, the boundary between rough iron and micro-inch accuracy was carved by hand. In the late 19th century, the American industrial heartland was a roar of soot, glowing blast furnaces, and horse-drawn wagons loaded with pig iron. Across Massachusetts, Connecticut, and Ohio, small workshops operated under the flicker of gas lamps. Factory floors vibrated under the heavy clanking of overhead leather belts connected to steam-driven line shafts. In this harsh environment, an elite group of toolmakers realized that industrial civilization was running into a wall. You cannot manufacture a precise steam engine without a precise lathe, but you cannot build a precise lathe without an even more accurate machine before it. Precision had to be bootstrapped from chaos. Industrial pioneers of extreme precision did not come from executive boardrooms. Most of these men started as 14-year-old apprentice shop sweepers, spending decades listening to the acoustic whine of cutting tools and feeling spindle heat with their bare palms. Consider F.W. Derbyshire and Louis Levin, who miniaturized the lathe for watchmakers and instrument builders. They proved that turning micro-components for timepieces required rigid beds and hardened steel collets capable of holding concentricity within a fraction of a hair. At the same time in Chicago, Franklin Hardinge was tinkering in his workshop, laying the foundation for the famous Hardinge cataract bench lathes. Hardinge understood that concentricity was the ultimate virtue. If a spindle ran out by even 5/10,000ths of an inch, micro drills would snap and delicate watch pivots would ruin. Turning across Europe, watchmaking precision followed a parallel track. In Switzerland, Schaublin introduced the legendary Schaublin 70 and Schaublin 102 toolroom lathes. These compact machines became the international benchmark for instrument makers, featuring ultra-precise headstock spindles and ground iron ways that turned microscopic components with breathtaking repeatability. Meanwhile in Boston, Edward Rivet founded the Rivet Lathe and Grinder Company with a fanatical devotion to mass. His Rivet 608 precision bench lathe became known among master machinists as the Rolls-Royce of small iron. It featured heavy, seasoned gray iron castings, hand-scraped ways, and an eccentric collet closer that allowed toolmakers to work to limits previously thought impossible. These early machines proved a fundamental rule of metalworking. Weight swallows vibration, and hand-scraping creates perfection. Unlike early small workshops, 20th-century factories accelerated into high-speed automotive and aviation production. Industrial demand shattered the limits of small bench lathes. Factories needed heavy machinery capable of taking aggressive cuts while maintaining toolroom accuracy. The line shaft era was dying, replaced by individual electric motor drives. This transition exposed a frustrating mechanical bottleneck. When electric motors were bolted directly to machine frames, their electrical hum transferred straight into the workpiece, leaving faint chatter marks on polished steel. Furthermore, machine beds flexed under heavy thermal loads. As friction heated the headstock, the iron expanded, throwing spindle alignment off by thousandths of an inch. Responding to this mechanical bottleneck, American foundries started an engineering renaissance that produced the most celebrated lathes in human history. In Hartford, Connecticut, Pratt Whitney unleashed the Model C toolroom lathe. The Model C was built like a fortress. Its wide bed casting was allowed to season outdoors in rain and snow for months to relieve internal stresses before final machining. Its headstock gears were ground to micro-inch tolerances, delivering silent power to a spindle turning on ultra-precision bearings. Engineers at the Hardinge Machine Company in Torrington, Connecticut, tackled thread-cutting accuracy with the Hardinge tool and gauge maker's lathe. Hardinge incorporated a unique sub-headstock tie-bar construction and a legendary lead screw reversing mechanism. With the flip of a single lever, a machinist could reverse the carriage without stopping the motor, allowing threads to be cut to dead-stop shoulders with absolute safety. Boston engineers answered with heavy precision in the form of the Rivet 1020S steelway. Rivet took gray cast iron and mounted solid, hardened tool steel ways directly onto the bed structure. The ways were ground and hand-lapped to within micro-inches of straightness. The 1020S was so heavy and rigid that it could turn hardened alloy steel as smoothly as butter. Over in Europe, master builders pushed their own boundaries. In the Netherlands, Hembrugge engineered the micro-turn lathe, utilizing specialized hydrostatic oil film bearings that floated the spindle on a pressurized film of oil, eliminating metal-to-metal contact. In Switzerland, Schaublin upgraded their benchmark design with the Schaublin 125, blending Swiss ergonomics with incredible geometric fidelity. Later, Hardinge perfected the HLVH toolroom lathe, featuring a single wide dovetail bedway that became the standard for modern prototype shops, which machine emerged as the undisputed king of American toolrooms. That title belonged to the Monarch 10EE, introduced in 1939 by the Monarch Machine Tool Company of Sydney, Ohio. The 10EE threw out traditional headstock gears, replacing them with an infinitely variable drive system powered by a Ward-Leonard generator and vacuum tube therotrons. The motor drove the spindle directly through smooth V-belts. A machinist could dial any speed from 40 to 4,000 revolutions per minute with zero gear vibration. Imagine trying to measure a tolerance of 1/10,000th of an inch. That is roughly 1/30th the thickness of a single sheet of printer paper. A human hair on the bed ways of a Monarch 10EE is a mountain compared to the oil film floating the carriage. Monarch integrated every process under one roof, pouring custom nickel iron alloys and hand-scraping mating surfaces for weeks until oil pockets held perfect lubrication films. Transparent upfront pricing and signed accuracy certificates guaranteed perfection. Inside factories during World War II, the true test of these machines came not in peaceful commercial trade, but in the white-hot crucible of global warfare. When World War II erupted, the Allied war effort required millions of artillery shells, complex bomb sights, radar components, and marine steam turbines. The United States government issued staggering production quotas to machine tool builders. Foundries in Ohio, Connecticut, and Massachusetts operated 24 hours a day, 7 days a week, under blackout curtains. Tens of thousands of workers, including women entering heavy industry for the first time, took their places behind Pratt Whitney Model CS, Hardinge toolroom lathes and Monarch 10 EEs. Clanking continuously day and night, elite foundries earned the prestigious Army-Navy award pennant for production excellence. But behind the public newsreels was a far more classified struggle. Deep within the secret laboratory city of Oak Ridge, Tennessee, and the isolated mesas of Los Alamos, New Mexico, scientists working on the Manhattan Project were attempting to construct the world's first atomic weapons. To enrich uranium and fashion precise plutonium implosion spheres, engineers needed to turn exotic, highly toxic radioactive metal to sub-thousandth of an inch tolerances. Standard commercial lathes could not handle the extreme friction and chemical volatility of these materials. Specialized Monarch 10 EE, Hardinge cataract, and rivet lathes were drafted into secret government service. Modified with custom dust extraction hoods and heavy bronze shielding, these machines ran continuously in sealed laboratories. Their massive cast iron frames absorbed the intense cutting pressure of uranium billets without deflecting a single micron. A failure in lathe precision meant a misshapen implosion lens, which meant a failed nuclear weapon. Throughout the darkest hours of global conflict, victory rested on the unyielding stiffness of hand-scraped toolroom beds. Foundries poured pig iron around the clock as train carloads of raw castings rolled into factory sidings. Machinists worked 16-hour shifts with blistered hands, knowing that a single chatter mark on a torpedo drive shaft could compromise an ocean patrol. The corporate owners took zero dividends during the war years, reinvesting every dollar back into factory capacity, apprentice training programs, and advanced metallurgical research. Precision was a weapon. They held the line. Cold War missile programs in the 1960s and 1970s pushed classical mechanical precision to its physical limit. Hand scraping could achieve tolerances of 50 millionths of an inch, but optical physics demanded something even more radical. The military needed massive parabolic mirrors for reconnaissance satellites, optical lenses for high-energy laser weapons, and precision spherical bearings for nuclear missile gyroscopes. Conventional grinding left micro-scratches on metal surfaces that scattered laser light. The solution was single-point diamond turning, using a flawless natural diamond gem shaped into a cutting edge to turn soft metals like copper and aluminum to a mirror finish straight off the lathe. Returning to the mysterious FBI intervention of 1984, the machine at the heart of federal concern was the large optics diamond turning machine, alongside its ultra-precision counterparts, the Precitech nanoform, the more nanotechnology turning systems, and the Lawrence Livermore LLNL Pearl II. The federal government realized that the LODTM was not just a laboratory experiment. It was the master key to the Strategic Defense Initiative, popularly known as Star Wars. The machine was designed to cut massive optical mirrors for space-based laser interceptors meant to destroy incoming missiles in flight. To achieve single-digit nanometer precision, the creators of the LODTM and LLNL Pearl II eliminated every environmental variable known to physics. The LODTM was constructed inside a custom concrete vault, isolated from ground vibrations by pneumatic air mounts. The entire structure was built around a 7-ton frame of granite and invar, a nickel-iron alloy with near-zero thermal expansion. Instead of ball bearings, the spindle floated on hydrostatic liquid oil bearings. The position of the diamond tool was monitored in real time by laser interferometers calculating distance based on the phase shift of light waves. If the temperature of the cooling oil shifted by even 0.005 of a degree, computer-controlled heat exchangers instantly adjusted the flow. The machine was so sensitive that the thermal radiation from a human standing nearby would trigger real-time tool compensation. The FBI classified the system because it allowed America to manufacture optical surfaces smooth to within atomic diameters. Man had mastered absolute geometry. The machine cut flawless parabolic optical mirrors directly from raw alloy billets with mathematical perfection. While American lathe technology reached its mechanical apex, the corporate world that gave birth to the industry was disintegrating from within. The late 1970s and 1980s ushered in an era of aggressive financialization, hostile corporate takeovers, and Wall Street private equity groups. Accountants who had never stepped onto a factory floor assumed control of historic machine tool enterprises. To short-term investors, the fanatical manufacturing standards of companies like Monarch, Hardinge, Pratt Whitney, and Rivet looked like financial waste. Why season iron castings outside for 6 months when you can pour thin gray iron and ship it immediately? Why spend 3 weeks hand-scraping carriageways when you can bolt on cheap plastic liners? During this same period, the Japanese machine tool surge hit the American market. Companies like Fanuc, Yamazaki Mazak, and Okuma flooded job shops with low-cost, mass-produced CNC lathes. While these imported machines lacked the multi-ton iron mass and 100-year durability of a Monarch 10EE or a Rivet 1020S, they offered automated G-code programming, rapid tool changers, and prices that domestic builders could not match. Stripping historic factory assets, private equity firms loaded legendary lathe brands with debt, selling off historic brick foundries for real estate developments, and outsourcing component manufacturing overseas. The Hardinge Machine Company closed its doors forever, its irreplaceable master blueprints discarded into dumpsters behind abandoned industrial shops. Pratt Whitney's machine tool division was carved up and liquidated by corporate liquidators. Rivet dissolved into history. Monarch struggled against bankruptcy, eventually shutting down its toolroom lathe production lines in Sydney, Ohio. The executive suites collected their performance bonuses and exited, leaving behind hollowed-out corporate shells. Boardrooms chose quick dividends over metallurgical permanence. They traded historical craftsmanship for short-term balance sheet profits. Corporate raiders dismantled century-old legacies for quick cash payouts. Corporate empires collapsed into financial ruin, yet the iron refused to follow them to the grave. Step inside any aerospace prototype facility, defense contractor job shop, or university physics department today, and you will witness a remarkable scene. Standing alongside million-dollar multi-axis CNC machining centers, you will find 50, 60, or 80-year-old Monarch 10EEs, Hardinge HLVHS, Pratt Whitney Model CS, and Schaublin 102s. Modern machinists buy these vintage heavy iron beasts from industrial auctions, strip away decades of old grease, and retrofit them with modern digital readouts and variable frequency inverter drives. Why do high-tech precision shops keep using vintage iron? Simple. No modern lightweight sheet metal lathe under $50,000 can match the vibration-dampening mass of a vintage hand-scraped cast iron bed. When a defense contractor needs to turn a one-of-a-kind titanium spindle for a satellite housing to within 50 millionths of an inch, they do not trust a flexible, lightweight imported machine. They step up to a 70-year-old Monarch 10EE or a Hardinge HLVH. The electric vacuum tubes may have been replaced by solid-state electronics, but the underlying gray iron, hand-scraped by American craftsmen nearly a century ago, remains as true and unyielding as the day it was poured. The company died. The machines did not. Thank you for watching Rivet and Rebar. If you enjoyed this deep dive into precision engineering history, hit like and subscribe. Up on your screen right now is our story on the lost art of hand-scraping master surface plates. Click it to keep exploring the iron that carved history.